This is part 2 of chapter 7, flow past immersed bodies or external flow. I should acknowledge that the following slides have been prepared using the fluid mechanics textbook of this course that we have used by Frank White. In the previous lecture, part 1 of this chapter 7, we started talking about the equations of the boundary layer. Oh, by the way, we only focus on laminar flow. In the turbulent flow, the equations will look different. So we said that in the boundary layer, a thin layer adjacent to the plate, we can write the continuity equation or conservation of mass, momentum equation or Navier-Stokes equation in x direction. This is for a Newtonian fluid, so we call the momentum equation as the Navier-Stokes equation. And the third equation is the momentum balance in y direction. So this is this plate in z direction is very long, so we can consider the boundary layer on a flat plate as a two-dimensional flow. So now the question is that how we're gonna deal with these equations. So in 1904, so in more than 100 years ago, some very nice approximations was made by Prandtl, and then the equations that you observed in the previous slide were significantly simplified. So that's based on several assumptions, and the assumption is that if the Reynolds number is large, then we will have a thin layer, a thin boundary layer, and if the boundary layer is thin compared to the length of the plate, then we can make some assumptions. So don't worry. So that then we will see some consequences. So again, the assumption is that Reynolds number is large, and this is equivalent to saying that the thickness of the boundary layer is very small compared to the length. So this will bring about several reasonable consequences or reasonable understanding. So first we realize that v, the vertical component of the velocity in the boundary layer, is much smaller than the horizontal component. Because the original flow is horizontal, there is some y component of the velocity, but it is very smaller than u, v much smaller than u. We can also make these arguments that the gradient of velocity in x direction, du dx, is much less than the gradient of velocity u in y direction. Because in y direction the thickness is only delta, the gradients are very large. So in a large distance, the velocity changes from 0 on the surface to capital U on the edge of the boundary layer. But in x, the gradient in u is not substantial. So this term is much smaller than this. And we can also say that the gradient of v with respect to x is much smaller than gradient of v with respect to y. And the reason is that the length of the tube x, if we assign a characteristic length to x, that would be L. The length of the tube is much smaller than the characteristic length assigned to y, which is the thickness of the boundary layer. And this is also equivalent to saying that Reynolds number is it can be proved that actually based on the assumption of having a thin boundary layer, Reynolds number is much larger than 1. So if we apply these assumptions, let's look at the third equation in the previous slide, the momentum balance in y direction. If you go back to the previous slide, you see that this is the same as, this is the momentum balance in y directions. Here we do have velocities v. So if you look at these terms, you see that For instance, here you have a partial v partial x, or dv dx partial. This v is very small. Then the second term, you have a v which is a small, another v which is a small, but this y is proportional to delta. It is not a, it is also a small. So this term overall is a small because of this v that we have. And then on the right side, we have the second derivative of v with respect to x. So its dimension is proportional to delta divided by length of the tube L squared. It is very small. And this one sort of small because you do have this is like this v is small, but this y is not small. But overall, because of v being small, this term is also small. Anyway, the bottom line is that all of these terms can be neglected because they are small, and neglected with respect to what? With respect to the terms that we do have in the x component of the Navier-Stokes equation. So with compared to those terms in the x component of the momentum equation, these terms are small. Otherwise, they are comparable to each other, right? So we need to be careful about what we are talking about. These are small compared to the previous terms. So what you see here is dp dy is therefore equal to 0, because if we neglect all other terms, the pressure does not change in y direction, so pressure is only a function of x. So in the boundary layer, pressure does not change much as we move vertically or normal to the plate up. Pressure changes, for now, changes only in x direction. Okay. So if we look at, if this is our plate, if this is our plate again, a flat plate, and this is our boundary layer. If you look at outside of this boundary layer, you can write the Bernoulli's equation. Outside of the boundary layer, there is no viscous effects, so there's no friction. Pressure term plus velocity term is equal to a constant. We have not considered the gravitational field. So if you take derivative of this Bernoulli's equation with respect to x, you will see dp dx, but since p is only a function of x, you can convert partial derivative to total derivative. It's equal to the derivative of the second term, which is u du dx. If you are considering a flat plate, which is the case here, so it means that for a flat plate, we do have an external flow with a uniform velocity, unless we use a different type of external flow. But basically what we have seen so far, our assumption is that a free stream with a constant velocity capital U approaches the plate. So this U, therefore, outside of the boundary layer does not change with x. So therefore this is equal to 0. So P does not gradient, so P does not change with x either. So it's like dp dx is constant, dp dx is 0, dp dy was 0, therefore P is constant. Okay, so now if we look at our equations again, the boundary equations in the boundary layer, so this is the continuity equation. The terms are comparable, du dx and dv dy. We cannot neglect any of these two terms. And then the x component of the Navier-Stokes equation, the first part is the acceleration. The second part had a pressure term, dpdx, which is equal to 0, so we don't have it. And then we had the second term. So on the right side, we had nu, the second derivative of u with respect to x, this term, and then the second derivative of u with respect to y. If you look at this equation, you see that because x is proportional to L, but y is proportional to delta, and delta is much smaller than L, so the second derivative, the second term, is much larger than the first term. So as a result, on the right side of the momentum equation in x direction, we only retain the larger term and neglect the smaller term. So this will result in this equation. So you see why we are doing this, because it simplifies these mathematical equations and provides a chance to be able to solve the equations. And don't forget that this was proposed more than 100 years ago. 100 years ago, there was no computer, there was no numerical simulation. Everything was analytical and experimental. So the equation that you see here, before that, let's look at the boundary conditions as well. So usually when we have differential equations, we need to specify boundary conditions in order to be able to go and solve the equation. So you remember from the course differential equation. So those partial differential equations are subjected to these boundary conditions on the wall at y equal to 0, which is on the wall. Both components of the velocities are 0, u equal to v equal to 0, no slip condition. And as y becomes equal to delta at each x, as y becomes equal to delta, we reach the boundary, we reach the edge of the boundary layer. So we said that at this point, u is equal to 99% of the free stream velocity, or is simply equal to that free stream velocity. So in the case of a flat plate, u is just a constant. So the solution for the equations in the previous slide, the boundary layer equations, were actually found by Prandtl's student, PhD student, Blasius, in 1908. So it's like about several years after the theory of the boundary layer, which was proposed by Prandtl, one of his students actually solved the equations mathematically. So how he solved it, well, I don't want, the details are in the book. So he basically converted those partial differential equations to an ordinary differential equation using a change in the variables, which is called similarity solution. So he converted the PDE into ODE, and then that ODE was simple enough to be solved using just like a numerical methods, but without the use of a computer. So based on this solution, which is good for laminar flow, he was able to find the, sorry, so if this is the boundary layer again, based on the solution, he was able to find the velocity profile in the boundary layer. And once the velocity profile is found, other parameters can be found as well. For instance, delta, the thickness of the boundary layer, was found by Blasius. So he showed that delta over x, thickness divided by x measured from the leading edge, is equal to this equation, 5 over Reynolds to the power of 1/2. So this is the thickness of boundary layer at x from the book. And in addition, he developed some other useful information. One is the skin friction coefficient. Skin friction coefficient is coefficient of the shear stress on the surface. So we said that because of the viscous effect, so as you see here, there is a shear stress on the surface. So if you remember, for a laminar flow, this shear stress is equal to what? It's equal to mu and then du dy. Sorry about the du dy from previous chapters, for instance, chapter 4. So this is the shear stress. So once the velocity profile is known, then you can go ahead and find the shear stress. So, and if you make this shear stress on the wall non-dimensionalized with respect to 1/2 rho u squared, dimensionless, then this becomes Cf, the skin friction coefficient. So we can show that Cf, skin friction coefficient, is equal to 0.664 divided by Reynolds number to the power of 1/2 for laminar flow. So don't forget that the boundary layer equations are only good for laminar flow. For turbulent flow, some modifications have to be done. So another useful piece of information is the drag coefficient. So when we have this, when we do our flat plate, we said that we do have tau on each x, at each location. So at each x, we can have that skin friction coefficient obtained from the previous equation in the previous slide, or tau. So if we rearrange the previous equation, we will see that tau at each given x is proportional or is equal to these values. A constant density, viscosity, velocity to the power of 1.5, and x square root of x to the power of 1/2. So we do have this shear stresses acting on any local position or at any local x. So if we put all of these taus together, all of these differential forces, then it will give us the drag force, the total force, which is like pushing the plate in the opposite direction of pushing the plate in the direction of the flow. So we do need a force in order to keep the plate in position. So that force, let's call it D, is the drag force. So the integral, therefore the integral of this tau in the direction of x, so the integral of tau in the direction of x, and when you multiply it by b being the width of this plate perpendicular to the screen. So this integral from x0 to x equal to x means from the beginning of the plate to any x for instance the end of the plate. So this integral would give us the drag force dx. So if we substitute tau from this equation up here and integrate with respect to x, everything else is a constant except for the x, so we can evaluate the integral. It's pretty much straightforward, and we can find the drag force from the leading edge to the any x, or to the trailing edge, which is like the end of the plate. So if we make it dimensionless, we divide d, and d for a plate which has a length L, but divided by 1/2 rho u square. So let's look at this here first. So we can go ahead and define a drag. We can go ahead and define a drag coefficient. So drag coefficient CD is simply drag force divided by 1/2 rho v squared a. So that's the velocity term. And then the second one is the area which we are dealing with. The area is the area of the plate. The area of the plate is simply BL. And then the other type part of it is 1/2 rho u squared. So CD, the drag coefficient for a flat plate, laminar flow on a flat plate, is therefore equal to this term, 1.328 over Reynolds L, length of the plate, to the power of 1/2. So if we compare it with the skin friction coefficient for a plate which has a length L, you see that CD is twice CFL. CD is the drag for the entire place, the drag coefficient for the entire place, but CF is only the local drag coefficient or skin friction coefficient. So it means that CFL is 1/2 of CD. What does it mean? It means that as you move forward in the direction of the flow, as x increases, so CF becomes 1/2. So it means that CF, the local friction coefficient, decreases as we move in x direction. And this can be seen here because tau is a function of 1 over x to the power of 1/2, inversely proportional. So as x increases, tau decreases. That's why CF decreases with x. So we talked about laminar flow, turbulent flow, and so far we have considered that if Reynolds number based on x is greater than 10 to the 6, it's turbulent. If less than 10 to the 6, it's laminar. It's not like a very strict number because there is a transition from laminar to turbulent. So when you have the boundary layer, when it's laminar, it's a very nice and laminar and orderly boundary layer, and then some fluctuations start, and then eventually it becomes more turbulent. So usually different books and different sources take different numbers for transition for laminar, for the border between laminar and turbulent. So here the book states that if we take the Rx transition 5 to the times 10 to the 5, then that's transition between laminar to turbulent. So that's good for typical commercial surfaces and for gusty-free streams. This is a realistic value for transition from laminar to turbulent. So do you remember the value for the transition Reynolds number in a pipe? In a pipe we had that less than 2100 the flow was laminar, then above 4000 it was turbulent, and then we said, okay, because there is really not much information in the transition region, we say that below 2300 we consider the flow to be laminar, and above 2300 we assume that it's be turbulent. So here is the same thing. So above 5 times 10 to the 5 we assume that it's turbulent. Below 5 times 10 to the 5 we assume that it's laminar. So the equations that we had based on the boundary layer theory and the Blasius solution are good for laminar flow. Reynolds number less than this number. Okay. So example 5.3 of the book, a sharp flat plate with L 50 centimeter and B 3 meters is parallel to a stream of velocity 2.5 meter per second. So we have the dimensions of the plate and the U, this velocity is like U, the free stream velocity U, 2.5. Find the drag on one side of the plate, because when you look at the plate, so if you look at like a plate, it has two sides, right? This became like a rifle. So if you have a flow over this, you have boundary layers on both sides. We need to be careful. In some cases, you have boundary layers on both sides, but in some cases, only one side is exposed to the free stream. So if only one side is exposed, just one side has to be considered. Here the question asks the drag on just one side. So it's like the other side is not exposed. Okay, so the assumption is that first let's calculate the Reynolds number to see whether we can use the laminar flow equations. We don't have turbulent flow equations yet, except for the beginning that we just showed the equations. So if we calculate Reynolds number, UL over mu of air, 83,000, it's less than 5 times 10 to the 5, so it's a laminar flow. So based on, we can go ahead and use the Blasius equations, delta over X or delta over L is equal to 5 Reynolds L to the 1/2. So delta, the thickness of the boundary layer at the trailing edge, this delta is therefore equal to 8.7 millimeters. So the length of this plate is 50 centimeters. So 50 centimeter, and the thickness of the boundary layer after this is 1/2 meter. The thickness is only 8 millimeter thick. So it's really thin. So if you want to find the drag force for this entire plate, the drag coefficient is found based on the equation given in the previous slides. So that's the drag coefficient. Then the drag force, if we want to find the drag force D on one side, we need to multiply the drag coefficient by 1/2 of rho U squared times the area of the plate, BL. So it becomes this value, 0.026 Newton. It's quite small. So this is a friction drag and it's very small for gases at low velocities. So we have air blown over a flat plate, 3 meters by 1/2 meter, and the friction, and this drag force is caused by friction. So because the air wants to push the plate, for instance, forward in its direction, but this drag force is really small. Then let's do the same problem, but this time for water instead of air. So for water, we use nu of water, and Reynolds number becomes, for the same plate, becomes 12.4 10 to the 6. So it's larger than 5 10 to the 5, but it's still close. So it's indeed in the transition region. So for now, we have not talked about the turbulent flow correlation. So for now, let's say that the plate is smooth. If the plate is smooth, then even at this Reynolds number, which is not higher than the transition Reynolds number, it still will remain laminar if the plate is smooth. Or for now, let's make an assumption, and then later that we talk about the turbulent flow correlations, then we should actually use the right correlation, turbulent flow correlation. So based on the laminar assumption for a smooth plate, delta over L is found again, and delta becomes uh, 0 delta becomes the thickness of the boundary layer becomes 2.2 millimeters. So if you remember, for the case of air it was 8 millimeters. In the case of water it is 2. So this is 4 times thinner than the air. Air results in part A due to the high laminar Reynolds number. So because the Reynolds number in this case was higher for water, therefore the higher the Reynolds number, the thinner the boundary layer. So now if we go ahead and find CD, so CD, we found CD, the drag coefficient. The drag coefficient is smaller than the drag coefficient of the case of the air. However, when you want to find the drag force, so the drag coefficient is smaller because in this case the Reynolds number is larger than the Reynolds number of air. But that's only the drag coefficient. But the drag force is different. So the drag force, you need to multiply CD by density of water, which is 1,000 times larger than the density of air. So the drag force associated with water, you should expect to be much larger, right? So if you multiply by the density of water, again U squared BL, same as before, the drag force becomes 5.6 Newton. So the drag is 217 times larger for water compared to air, although CD of water is lower than CD of air, reflecting that water is 55 times excuse me, water is 56 times more viscous and 830 times denser than air. So I mentioned about the viscosity that appears, the density that appears in this equation for drag. We should also consider the fact that water is more viscous. And all right, so so if for instance the plate is, if the plate is like not smooth, then we would need to go ahead and use the correlations for turbulent flow that we will talk about in the following slides. So for turbulent boundary layer equations, so we are not going to talk about the modeling, we just show the equations. So these are turbulent boundary layer equations on a smooth flat plate. So the Reynolds number, the Reynolds number is larger than 5, like 10 to the 5 or 10 to the 6. It's like to be consistent, 10 times 10 to the 5. So for this case, delta over x is obtained using this equation. This equation was also given in the beginning of this chapter, just to open the chapter. But this is delta over x for a turbulent flow, which is different than the equation for delta over x for a laminar flow. This is also equivalent to this equation. Reynolds in terms of delta, the characteristic length, because Reynolds does have a characteristic length, right? So Reynolds in terms of delta is equal to 0.16 Reynolds in terms of x to the power of 6 over 7. So usually this is the preferred form of using this equation to find delta. Similar equations for skin friction coefficient CF at a given x, but different coefficients and different power of the Reynolds, 1/7. And similarly for CD, the drag coefficient is 0.031 Reynolds to the power of 1/7. So this is 7/6 times the CFL. So for laminar flow, this CD was, if I remember correct, for laminar flow, CD was like twice CF. Here is 7/6. All right, so let's stop here. This lecture is becoming too long. So let's stop on this slide and then we will continue from this slide in the part 3 of this lecture, of this chapter.